in the meantime to talk something.
You're rolling, Doctor. You may proceed.
Thank you. So we talk about Galerkin's method. So 26, Galerkin method revisited. Okay. So we can actually say in general terms, we discuss it in more general form. Okay, and I will tell you how. Imagine we have a differential equation. So I will denote it like this. L of W equals 0. So this is derivatives and everything, plus boundary conditions. At the ends of the beam or rod or column or plate or shell or three-dimensional solid body. Okay? If and when I'm going a bit fast, then you tell me and I will slow down. So usually, okay, what happens with this is solutions. Solutions to the problem. Okay. Some problems have closed form solution. Okay, some problems. Now some problems have maybe, say, series solution. But many problems are too difficult to have an exact solution. So in this particular case, we resort to approximate solutions. Okay, so majority of the problems of vibration problems are not amenable to exact solution. Okay. Majority of the problems. We can even say, if you want, overwhelming majority. So therefore, there are approximate methods. Therefore, humankind has developed approximate methods. So I will give you some methods that some of these are approximate methods. this Galerkin method. Rayleigh's method. Ritz method. Ritz method. So these last two are Nobel Prize winners in physics, but they dealt also with mechanics a lot. Then finite element method. Okay, finite element. Then FDM, finite difference method. Six, collocation method. Seven, differential quadrature method. And then I will boundary element method. Asymptotic method. Okay, so that is, there are many more methods actually. But this is more or less the, if you want, a supermarket of approximate methods. Okay. Are we done with this? Yes. So 3. So Galerkin, idea of Galerkin method, as I said, idea of Galerkin method is as follows. We can construct some set of functions that satisfy boundary conditions, but not differential equation. So these are functions, say psi1 of x, psi2 of x, psi3 of x, etc. Then we approximate the sought displacement as, so W of x is approximated as k from 1 to n, a k times psi k of x. So ak is not known. We need to find. Paying attention that this writing already is already paradoxical. Why? Why do you think it is paradoxical? Because we don't know the solution. But we tell the solution. You, hey, the solution. You better behave as k from 1 to n a k psi k of x. I'm prescribing the solution. I'm telling you, you know what, I don't know you, but I will approximate you. I will approximate you as a finite sum of some functions that I do know. Okay? So you are actually linear combination of some functions that I know. Now I will tell you how much ak should be. Okay? So that is how. Now the question is, what is this n? N is number of terms taken into account. Okay? So I can take one term, two terms, etc., etc. So then what we do is as follows. 4. We substitute this w equals k from 1 to n, a k psi k of x, into L of w equals 0. We get L. This is not Laplace transform. This is some Gothic L I'm using. Summation a k psi k, k from 1 to n, naturally is not 0. Because if it was 0, then I solved the problem and I don't need to do anything. If it equals 0, I'm done. I hit upon the exact solution. Because it's this psi satisfy boundary conditions. Now I put this here, this is 0. I finish the problem. I just guessed the solution. You know? Maybe in the future some genius will tell us, you know what, you don't need to solve. Just take, I'll tell you how to take a's, put this a's like this, and you put this psi's and you're done. You don't have to do anything. Maybe there will be some unbelievable idea. Not yet. So since L of ak psi k does not equal 0, so we can denote it as error. And so that is epsilon. Okay, so that is an error. So now let us imagine, just imagine, psi k to be coordinates. I mean, that's unbelievable to imagine, but these are functions actually. But this is psi 1, psi 2, say psi 3. This is 0. Okay, imagine for 1 second, forget now these are functions. Imagine we denote them like coordinates. By the way, they are called, psi k is a coordinate function. That is how Galerkin called them. Coordinate functions. Now, therefore, error itself, Where is my red pen? Where did red pen go? That's no. Okay. So then error is not 0. So this error is, say, something like this. So that is an error. So now we want error not to be seen in these directions. I don't want to see this error in these psi1, psi2, psi3 directions. Now, how it is possible? I just have to project error in psi-y direction, and that should be 0. So what I do is as follows. 5, we say projection of epsilon onto psi1 must be 0. Likewise, projection of epsilon onto psi2 must be 0. Projection of epsilon onto psi3 must be 0. So how do we calculate the projection? So we say epsilon psi1 dx from 0 to L equals 0. Or we write down epsilon psi1 equals 0. So that is an abbreviation of this. Epsilon times psi1 dx must be 0. That is this condition, Galerkin's condition. Then epsilon psi2 dx must be 0. Or epsilon psi2 must be 0. Then epsilon psi3 from 0 to L dx must be 0. Or epsilon psi3 must be 0. It's a very beautiful idea. I mean, unbelievable idea. This is like, as I already mentioned, that, say, child makes an error, but very often mom and dad and grandmother and grandfather do not see this error. They overlook it. Okay? In their coordinate system, their child is error-free. He's the best behaving child. They don't see these errors. Only others may see, but they don't see these errors. So that is actually what happens. So Galerkin, as if, I mean, he did not say this, of course, but as it were, I mean, described family of functions and how they behave, how this error behaves in this family. Okay? Once this gives me an set of equations for A sub k. Then I substitute this A sub k, W equals A sub k times psi k, k from 1 to n. So I found the solution. So this is a solution in which error is not seen from some coordinate functions. Okay? That is what happens. Yeah, these are dot products. Yeah, let me write down. Dot products or inner products or scalar products. Okay, in various countries we use different different word. In the United States, we use dot product. Okay, in Europe, they say scalar product, scalar product, because the result is a number, 0, not a vector, something like that. Say it again? Yes, like energy or temperature. So from if there are eyes here, that means, so from these eyes we don't see this. So from these eyes also we don't see this. And from these eyes also we don't see this error. So what it says is as follows. Error is not 0, but we don't want to see that error in some directions. It is not 0. Again, it is not 0, of course, because I know that, I cannot solve the problem exactly. But at least from some directions you don't feel it. So therefore it is closest to be 0. So you may want to write this idea. Error is not 0, but from some directions you don't feel it. So it behaves as if it was 0. As if. Okay, now 5. So what is our topic number now? 27, yes? Constructing first coordinate system, coordinate function for simply supported beam. So this is this beam. W equals 0, W second derivative equals 0. W equals 0, W second derivative equals 0. This is L. Now we have 4 boundary conditions. So psi 1 must satisfy them. So now in question, what order polynomial means simplest function should we have to satisfy 4 boundary conditions? What kind of order of polynomial I should have? Second order? By no means. A student says second order. Let me write down A1, second order. Will be, say, A1 plus A2x plus A3x squared. This cannot, how many boundary conditions can we satisfy? There are 3 constants only that we want to find here. But I have 4 conditions. Can I find 3 constants for 4 conditions? Okay, so no. Answer is no. A2. So another student suggests 4th order equation. 4th order polynomial. So that will be say A1 plus A2x plus A3x squared plus A4x cubed plus A5x in 4. So let us write psi 1 of x equals this. And let us see what happens. So now I want to satisfy boundary conditions. Forget the differential equation. Later I will do with Galerkin formalism. So psi at 0 must be 0, yes, because W, what is W now? W equals A1 psi 1, is it right? One term, I said. N equals 1. So I'm using only one term. Each of the functions should satisfy boundary condition. So at 0 equals 0, I substitute here A1 must be 0, because these all fall. So this is 0. Now, psi 1 first derivative equals A2 plus 2A3x plus 3A4x squared plus 4A5x cubed. Now, psi 1 second derivative equals 2A3 plus 6A4x plus 12A5x squared. Now, this psi 1 at 0 must be 0. So A3 must be 0. So A3 is 0. Now we are left with following. So then psi 1 equals actually, look, A1 and A3 equals 0. So A2x plus A4x cubed plus A5x in fourth power. That is what we are left. Now boundary conditions. Psi 1 at L must be 0. So that will be A2L plus A4L cubed plus A5L in fourth power must be 0. You agree? Am I going too fast? No. Then psi 1 second derivative at L must be 0. So from here I get this. 2 times, but A3 we showed that 0. 6A4L plus 12A5L squared equals 0. So I have two equations. So I will write down then, look, from here I see A4 equals minus 12A5L squared divided by 6L. So it's minus 2A5L. That is A4. Then I substitute this here and I get A2L plus A4, but I will substitute this minus 2A5L plus, and then it is A4 and multiply this by L cubed. Then plus A5L in fourth power equals 0. So I get A2L minus 2 plus 1. So it's A5L in fourth power equals 0. So A2 equals A5L cubed. So then what I get is as follows. Look, psi 1 of x equals. I substitute this back. A1 is 0. So A2, instead of A2, I write A5L cubed. So A2 is multiplied by x. Then A3 is 0 plus A4. A4 is minus 2A5L, and that is multiplied by x cubed. A4, yes. Then plus A5x in fourth power. So this is what I got. Now this actually can be write this. Psi 1 of x equals then. I would like to introduce non-dimensional coordinate psi. So that is like this. Equals x over L. If that is the case, then x equals psi times L. And I substitute this here. I get A5 L cubed x. So that is xi times L minus 2a5L. Then it is xi cubed, which is x cubed. So xi cubed, L cubed, plus a5, x in fourth power, xi 4, L in 4. So then it gives me psi1 of x equals a5 L in fourth power xi minus 2a5 L in fourth power xi cubed plus a5 L in fourth power xi in fourth power. So everywhere I have this a5 L in fourth power. So I take it equals 1 because I just want the function. I just want the function itself. So psi1 of xi, or x if you want, equals xi minus 2 xi cubed plus xi in fourth power. Or if you want to write x over L minus 2x over L cubed plus x over L in fourth power. So we found this first function. Now I will give you a homework. Oh no, homework set. What is the set number? 15? 14. Find the approximate value of first natural frequency of a simply supported beam so this is first problem using psi1 equals x over L minus 2x over L cubed plus x over L in fourth power. Compare with the exact solution. Calculate percentage-wise difference. Second, find psi1 for clamped beam. Any questions? Okay, if there are no questions, rest of the class I will be here naturally. We will watch some presentation on the video. I will have to tell them. Where did I put this right? This is not music. Tacoma Narrows Bridge. So first is axial vibration. Second, this is axial vibration. Exactly what we got. Mass on the spring. This is transverse vibration of a beam. In this case, beam. This is torsional vibration of a shaft. So that is the pendulum. So various kinds of vibrations. So again, this axial vibration. So if we measure where it is at different times, so that's the picture that we get. Omega t plus epsilon, because at t equals 0, so we get that this number is a value equals some sign of some epsilon. It did not start with 0. If it starts with 0, then epsilon is 0. So this is a period, of course, because it repeats. Somehow this picture is not very good because amplitude is bigger in reality than the picture. So this is an amplitude, plus C minus. And this C must be big C on the left. Different initial conditions. Frequency depends only on the characteristics of the system. See, in the first the amplitude is bigger, frequency seems to be the same. So only K over M is the same. Oh, no, this is also good. If you shift a bit on the line, damped. Now this mass is in some liquid. See until it decreases and decreases. So this is both damping on the right and spring on the left. I don't know if that as a critical damping. So initial condition led to smaller displacement. That is critical damping. Critical damping, there is no oscillations, it goes to zero. Damping ratio is that. Very big. So support is being removed. Yeah, bigger than less of the resonance. First of all, there is no resonance there, but there is maximum. Misalignment also acts as forced excitation.